Hello and welcome back to another video on differential equations, which is that specific section of Advanced Engineering Math 1, which we are covering. Once again, the linear, which you will also be doing in Advanced Engineering Math 1, will be covered in a separate playlist, and then eventually we will get to use that with a bunch of fun stuff. So up till now, in the previous video, we covered a good chunk of information in terms of the definitions and terminology that we need to know to be able to work with our differential equations. So how to classify them based on whether they're ordinary or whether they're partial, so their type, as well as their order. And some general forms we want to know as well. If at any time anybody has any questions or content that they would like covered, feel free to reach out in the comment section and let me know. And I also plan on putting together a separate video after we finish up this section just to work with the material a little more and get some clarification on everything. So without further ado, let's get started. So before we talked a lot about different forms and terms and stuff, but now we're actually going to talk about the solution of an ordinary differential equation. So any function phi that is defined on an interval I and possesses at minimum n continuous derivatives on this interval I, and when substituting phi into an nth order ordinary differential equation reduces the equation into an identity, is a solution of the differential equation on that interval. So that's a lot, to say the least. And of course, it's hard to just read a bunch of words and understand exactly what that means. So let's break this down a little bit. So from before, let's recall the general form of an nth order differential equation, right? Expressed in one dependent variable. That's f of x, y, y prime, all the way up to that nth order, right? Our nth derivative of y is equal to 0. So now, what this definition is actually saying is that we have f of x, phi of x, phi prime of x, again, all the way up to that nth derivative, x is equal to 0 for all x on I. So now just looking at this, you might look and say, well, then what's the difference between y and phi of x? Well, primarily what we're getting concerned with now is this interval I, right? So without getting too much into it now, we're going to make more sense of this later with some examples, but you can essentially think of phi of x as y. And once again, we'll get into it and explain this more. So now we have y equals e to the 0.1x squared as a solution to the differential equation dy over dx is equal to 0.2xy. Alright, so now let's talk more about this interval I. I is called the interval of definition, interval of validity, or the domain of the solution. These are all interchangeable, they mean the same thing, right? So now that we know how we can classify I, we're going to see if we can verify this function up here is a solution to our differential equation on the interval negative infinity to infinity. All right. So what we're going to do, again, based on that definition, that said that phi of x can be substituted into the differential equation and reduce it to an identity. So an identity, right, we're trying to make one side equal the other. So let's start out by doing a left-hand side substitution approach. All right, so let's see, we had dy dx on our left-hand side. So dy dx is equal to the derivative of our solution function y, which was e to the 0.1 x squared. So now use a little chain rule. 0.1 e to the 0.1 x squared and 2x. So now this is equal to 0.2 x e to the 0.1 x squared. All right. So now let's do our right-hand side substitution approach. So we have 0.2 xy is equal to 0.2x, and now we're just going to plug in y, which is e to the 0.1 x squared. E to the 0.1 x squared. Alright, so we have successfully shown now with the substitution method that by attaining the same terms on the left and the right via this substitution, again, this is what an identity is, we also verified that each side is going to be the same for all real values of x. And it's all real values of x because the solution e to the 0.1 x squared is itself defined for all real values of x as well. And we will get into more detail on what that means. Alright. So now, let's take y equals x e to the x, right, which is a solution to our dE y double prime minus 2y prime plus y is equal to 0. So before we substitute, let's take our derivatives. So d over dx of y, and y is x e to the x, and that's going to be equal to, we're going to use product rule here, so x e to the x plus e to the x. Alright, and then the second derivative is just going to be the derivative of our first derivative. So that's just going to be derivative of x e to the x plus e to the x, which is equal to x e to the x plus 2e to the x, right? Because we're just doing a product rule again here. So the differentiation of this term here is just going to give us the same as this term, and then we just have to add the derivative of e to the x, which is just e to the x, so that's where this 2e to the x comes from. Alright, so now that we did that, let's go ahead and do our substitution. So we have y double prime, so that's going to be our x e to the x plus 2 e to the x minus 2 times y prime. Now y prime is just x e to the x plus e to the x, and I'm actually going to go ahead and just write these in here for clarification. Y double prime. Alright, so 2 x e to the x minus 2 e to the x, and then plus y, and y is just x e to the x. Alright, so this is going to cancel with this, and then we have 2 x e to the x's and 1 minus 2 x e to the x. So those are all going to cancel. we're just going to get 0. And with our right-hand side, all we have is 0. So that's all it is. So we've used this identity, right, this substitution that has reduced this down to a 0 equals 0 identity. The left-hand side equals the right-hand side. So this shows that on our interval -infinity to infinity, our solution function y equals xe to the x is, in fact, a solution on that interval. So now getting back to phi of x, we can just think of phi of x as equal to y, right? It's just the terms on the right-hand side expressed in terms of x. And having those terms expressed only in terms of x allows us to plug in and just manipulate each side and reduce it all the way down to an identity to verify that it is in fact a solution on our interval. An additional thing to note as well, the solution function y equals 0 is called the trivial solution, right? So for both of our previous examples, y equals 0 is a solution function, but it is called the trivial solution, also can be referred to as if your solution is identically 0, all that means is that it's just straight up 0. That's it, period. So the solution curve, right, is the graph of the solution phi of an ordinary differential equation. So let's consider our solution equation y equals 1 over x, which again, solution to x, y prime plus y is equal to 0. What are the intervals, right? So from before, one thing that you may have noticed is that both of our functions in terms of x, right, within the solution equation, they were continuous on -infinity to infinity. So all real numbers of x, that is their domains. But 1 over x, that's not the case. We have this vertical asymptote at 0, where the denominator equals 0, x equals 0. And once again, the domain for this is therefore going to be all real numbers except 0. So, from that, this means that our interval, right, that our solution function is in fact a solution to our differential equation is valid on, has to be any numbers except x equals 0. Now, that can be -3 to -2, 10 to 100, but why not just span the biggest interval we can as needed? So we're always going to want to do that. So regardless of what any initial conditions and initial value problems or boundary values in boundary value problems are, which again we'll cover later, we're going to want to have the largest interval possible to work with. So that's just a habit we need to get into. So 1 over x can be our solution on the intervals -infinity to 0 or 0 to positive infinity. All right. So now let's go back to y equals 1 over x. All right. Let's take the same substitution approach and create this identity. All right. So first, let's take the derivative of y. So the derivative of 1 over x, and that's going to be equal to -1 over x squared. So now, if we take the left-hand side approach, we're going to have x times -1 over x squared plus y, and y is just 1 over x, and this x is going to chop this denominator down into a power of 1, and then negative 1 over x plus 1 over x is just equal to 0. And on the right hand side, we just have 0. Alright, so once again, this now satisfies that 1 over x can be called phi. Right, so we can say that y is equal to 1 over x, which is equal to phi of x. And another thing to consider too, you know what, let's actually get our definition back here. So any function phi that is defined on an interval I, and again, it's defined on either negative infinity to 0 or 0 to infinity, and possesses a at minimum n continuous derivatives on this interval. So here n is equal to 1 from y prime. Our highest derivative is the first derivative. Okay, so if we think about negative 1 over x squared, right, that's going to be something like that. Let me do a little better there. Okay, so on our intervals that we are considering, the derivatives that we need up to n are in fact continuous, so that checks out. And when we substituted phi into our ordinary differential equation, it did reduce it to an identity. We got both sides equal to 0. So therefore, y equals 1 over x, and again, can also be considered just phi of x, is a solution of that differential equation on that interval. So the really important thing to take away here is that there is a difference between the graph of the function itself and the graph of the solution, right? It can be the same exact terms, 1 over x, but all we're considering, let's say we just want our interval 0 to infinity, right? What we're considering is 0 to infinity, therefore we just want this portion of the graph. Alright, so in terms of the solution curve, if our interval is 0 to infinity, this is not part of it. Okay, it's not part of it. So up until now we've been considering explicit solutions to our differential equations, but let's also evaluate and consider what an implicit solution of an ordinary differential equation is. So the formal definition: a relation g of x and y is equal to 0, and mind you that's a relation, so not a function, is an implicit solution to an ordinary differential equation on an interval I if there's at least one function phi that satisfies both the relation g of x, y equals 0 and the differential equation on I. So let's unpack this a little bit, starting out here. So if the relation has at least one function phi, right? So if we can, out of that relation, get one function phi that satisfies both the relation and the dE on I, and there's at least one, then we have an implicit solution to the ordinary differential equation on said interval. And in this sense, like we said before, we're considering that function phi of the form y equals phi of x. And that right there is explicit. So we need to be able to get an explicit solution of the form y equals phi of x from the relation, and it has to satisfy that relation as well as the differential equation. So, without further ado, let's look at an example. So x squared plus y squared equals 1 is an implicit solution of dy over dx is equal to negative x over y on the interval -1 is less than x is less than 1. So lo and behold, we have our unit circle here, and the unit circle itself is an implicit solution to this differential equation here, right? So one thing we can do, one strategy we can take, is actually using the calculus, method we learned in Calculus 1, which is implicit differentiation, the relation, and see if in fact we can derive our way to this differential equation. So we're going to differentiate this guy here, implicitly of course. So we're going to have the derivative of x squared plus the derivative of y squared is equal to the derivative of 1. Alright, so we know, do a little better than that, there we go. So we know that the derivative with respect to x is derivative with respect to x of x squared is just 2x. We know that the derivative with respect to x of 1, or any constant for that matter, is just 0. But what about this guy here? So what we're actually going to do is we're going to treat this as y of x, y as a function of x, which in itself is going to be squared. So then we are going to utilize chain rule for that. So the derivative with respect to x of y of x quantity squared is going to be equal, so derivative of the outer function, which we can just consider some variable with respect to x squared, which again, like we had before, is going to be 2x, or excuse me, not 2x. This is just going to be 2y of x times the derivative of the interior, so y prime of x. But we can now just, again, this y of x is for visualization purposes and understanding how this implicit differentiation is happening. We can change this y prime of x to the Leibniz notation and just rewrite this 2y of x as 2y. So this is equal to 2y times dy over dx. Alright, so then that means that all of this, alright, so we have 2x plus 2y dy dx is equal to 0. Let's subtract 2x from both sides. And we then have 2y dy dx is equal to negative 2x. And then with that, we can divide by 2y on both sides. That's going to cancel there. Okay. We have dy over dx is equal to negative x over y, which is the same as our original differential equation from before. But now, remember what we're looking for. We're looking for at least one function phi of x that satisfies both the relation and the differential equation on I. So let's take x squared plus y squared equals 1 and solve for y. So we're going to subtract x squared. Y squared is equal to 1 minus x squared. We're going to take the square root. have two solutions. Y is equal to plus minus the square root of 1 minus x squared. Alright, so this can actually be written as, let's say, y is equal to phi 1 of x, which is equal to positive square root of 1 minus x squared. And y is also equal to phi 2 of x, our second solution, which is equal to the negative square root of 1 minus x squared. So now we have our potential phi's of x. So we need to have both of these, right? Both solutions of phi of x satisfy both the relation as well as the differential equation. So let's go about doing that. So in terms of satisfying the relation, we'll work with phi 1 of x first. So let's take our left-hand side substitution approach. So we have x squared plus y squared, but we're saying that y is also equal to phi 1 of x. So square root of 1 minus x squared quantity squared, which is equal to x squared plus this squared is just going to simply cancel that square root. So it's just plus 1 minus x squared. We have both of these x squareds here, so those are going to cancel, and that's just going to be equal to 1. So now take our right hand side, and that's just 1, and that's it. So we verified that phi 1 of x does in fact satisfy the relation that we were given in the beginning. X squared plus y squared equals 1. So now let's take a look at phi 2. So we're going to have x squared plus negative square root of 1 minus x squared quantity squared. And the only difference here we have is this negative sign. But regardless of that, a negative times a negative is always going to be a positive. So we're going to have the same exact result as before. X squared plus 1 minus x squared, which is just equal to 1. And our right hand side is just 1. So we have shown that this does in fact satisfy the relation. So we're good here and here. Now we also need to satisfy our differential equation. So let's go with our substitution method. Again, starting out with phi 1 of x. So our left-hand side substitution approach. So we have dy dx, which is equal now to the derivative, with respect to x of course, of the square root of 1 minus x squared. So here we have some more chain rule action. So we have the derivative of the square root of whatever is inside, right? So that's just going to be 1 over 2 times the square root of 1 minus x squared. Right? The 1/2 portion is, of course, from the fact that the square root is the equivalent of a term to the 1/2 power. And then, of course, we just have to plop whatever is here in our original root on the bottom, because now it's negative 1 minus x squared to the negative 1/2, meaning that our square root is in the denominator. So now we're multiplying by the derivative of the interior. Derivative of 1 is just 0. Derivative of negative x squared is going to be 2x. So our 2's are going to cancel. We're just going to have x negative 2x. So we're going to have negative x divided by square root of 1 minus x squared. So now let's take our right-hand side approach. Alright, so that was originally negative x over y, which we are now saying is equal to negative x here, divided by, we're substituting in the square root of 1 minus x squared. And that's it. That's good. I can actually even just erase these parentheses, because these are exactly equivalent. So now let's go to phi 2 of x. Take our right-hand side approach here. So we have dy over dx is equal to the derivative with respect to x of negative square root of 1 minus x squared. And we know what this is going to be. It's just going to have the opposite sign, right? So that's just going to be equal to x divided by the square root of 1 minus x squared. Here, oh, I'm sorry. This is the left-hand side approach, not the right-hand side approach. My apologies. So now we're going to do the right-hand side approach, which is just going to be negative x over y, which is equal to negative there. That's all under x, right? So these negatives are going to cancel. Oh, I'm sorry. Man, 2 mistakes. Not my night. That's x over 1 minus the square root of x squared to the 1/2 power, or under the square root. And then here these negatives are going to cancel, and we're just going to have x divided by the square root of 1 minus x squared. So we've now verified that both of our solutions that we pulled from our relation, phi 1 of x and phi 2 of x, do satisfy the relation. They also satisfy the differential equation. So therefore, we can say that our g of x and y, being x squared plus y squared equals 1, is in fact an implicit solution to our differential equation. And here I graphically just have the 2 solution curves we have. So again, we have our interval of consideration, right? So they are in fact excuse me, valid solutions on said interval. Of course, that's without actually including -1 and +1, because there we would have vertical tangents as well, the very end of our semicircles here. So, and if you think about it, any relation of this form, right? Any relation of the form x squared plus y squared minus c is equal to 0, right? All we're doing is just moving whatever constant on the right side that was originally on the right side over to the left will formally satisfy dy over dx equals -x divided by y on the interval negative constant is less than x, which is less positive constant. But however, before we said that our phi of x is a real valued function. So let's consider something. Now here, we can already look at this and just see, based on the negative 25, right, that this is going to be producing a complex, no, not necessarily complex solution, I'm not going to get into it, but it's producing an imaginary number because there's a negative under the root. Remember we said that so here, our C would be negative. So that would be on an interval that would always make x, right? That would always make x equal to or less than. And it's not inclusive. So therefore, we are going to have imaginary numbers throughout, and we're not going to get into saying that, it's an implicit solution, but it's kind of not. So it's important to make that distinction. And although this is a good exercise and good example in order to prove this, actually formally finding the solution that is a relation is something beyond the scope of what we're going to be covering in terms of this material. It's not necessarily that there isn't a implicit solution that isn't good enough, but we might not necessarily yet be able to solve for that relation, g of x and y equals 0, using our analytic methods, because our phi of x, remember we are saying, is a solution of y. We can manipulate that algebraically however we want. We can evaluate it. We can differentiate it without any trouble at all. Alright? Now let's consider what a family of solutions to a differential equation is. Alright, so let's think back to calculus, primarily, of course, calculus 2, with integration. So when we're dealing with indefinite integrals, right, they require a constant of integration, c. So if we have integral of cosine x dx, that's equal to sine of x plus c. And of course, that c is to compensate for any constants we could have lost in differentiation, because the derivative of sine of x is obviously cosine of x, but if we have the derivative of sine of x plus any constant, let's just say 4, right, then that's just going to also be equal to sine of x, because the derivative of the constant itself is 0. Now, when we're solving a first order differential equation of the form f of x, y prime is equal to 0, right, and this is representing our differential equation, we usually get an arbitrary parameter or constant c in the solution. Alright, so then that means that this solution is represented by g of x, y, and c, which is equal to 0. And then this g here, that actually looks a little bit like a 6, so I'm going to fix that there. This g here, of course, represents our solution function. Now, mind you, this is just notation-wise. This doesn't, have anything to do with our g of x and y relation that specifically we went over with implicit differentiation. So this is not an implicit solution. This is just generally the solution to our f of x, y, and y prime from above. So this is a one parameter family of solutions. Okay, one parameter family of solutions, and that parameter is C. So when solving now, again, this was for a first order differential equation. So now when solving an nth order differential equation of the form f of x, y prime, all the way to our highest derivative, y to the n equals 0, this requires an n parameter, right? Requires n parameter family of solutions. N parameters. So we're going to have potentially as many parameters as we do the highest derivative. So, if you have a second order differential equation, right, then that would require a 2-parameter family of solutions. And this is going to be of the form g of x, y, c1, c2, all the way to c to the n, corresponding with, again, the total number. So if this is a 4th order differential equation, right, then we are going to have these 4 parameters, c1, c2, c3, up to c4. All right. Of course, equal to 0. So this means that a single differential equation can actually have an infinite number of solutions which correspond to any choice in said parameters to the differential equation. Now, a solution to a differential equation without any arbitrary parameters is considered a particular solution. So when, again, we have a solution that is free of arbitrary parameters, right? No C. That is a particular solution. So let's consider the second order differential equation. Y double prime minus 2y plus y is equal to 0. All right, and this should look familiar from before because we worked with this example to verify a solution to this, right, earlier via our substitution method. So verified solution, and that solution was y is equal to x e to the x on I negative infinity to positive infinity all real numbers. Well, now let's consider the family of solutions corresponding to this differential equation. And that is going to be y is equal to c1 e to the x plus c2 x e to the x. And if we look at this, we have our x e to the x, which was a verified solution, right? And y equals x e to the x is in fact a solution and didn't have any c in front of it. All right, so that we can consider a particular solution. But now this solution equation here is not just a singular solution. It represents the entire family of solutions for this. So now let's consider this graph of a few solutions. I know it's very hard to see, but there actually is in fact a blue horizontal line representing a solution to this differential equation here. All right. And that would correspond to y equals 0. So if we look back to our family of solutions, that would be when C1 equals C2, which is equal to 0. Okay? Now, let's also consider when y is just equal to x e to the x. Well, like I said, we evaluated that before, so that's just going to be when C1 is equal to 0 and C2 is equal to x e to the x. All right. And we could also have when C2, or let's say C1 is equal to 1 and C2 is equal, oh, I'm sorry, it's not when C2 is equal x e to x. C2 is equal to 1, therefore 1 times x e to the x is x e to the x. And in this set, C2 is equal to 0. So that would just give y equals e to the x. And let me actually just write these all out. So this would correspond with y equals e to the x. This would correspond with y equals x e to the x. And we can also consider when C1 is equal to C2, which is equal to 1, which then y is equal to e to the x plus x e to the x. So now we see what a family of solutions to a differential equation is, and that it represents an infinite amount of solutions to our DE based on the choice in this arbitrary parameter or parameters. In this specific case, we can choose any values for these, any values, but when later down the road we have initial values, right, corresponding maybe to, you know, the actual physical model of some system or mechanism of some sort, then those will actually have not only meaning to them, but those will provide us a means for finding a particular solution based on those initial conditions, right? Because we will then use those to actually solve for C1 and C2, or however many parameters we have. Another important thing to note is a singular solution to a differential equation. Now, a singular solution is when we have, say, a family of solutions to a differential equation, but then we also have a satisfactory solution to that differential equation that can't be obtained by specializing or by selecting any set of parameters. So therefore, that is called a singular solution. All right. Moving on. Finally, the last part of this section here would be a system of ordinary differential equations. And like I was talking about before, when we could have initial values for actual representation of modeling systems, and differential equations is extremely powerful. It's, especially for engineers, one of the most powerful tools you have in your mathematics back pocket in order to represent actual real-life scenarios, circumstances, systems, whatever they may be, with mathematics. So a system of ordinary differential equations is at least two or more equations that have the derivative of two or more unknown functions of a single independent variable. All right, so let's consider x and y. So we can say that dx dt equals f, which is a function of t, x, and y, and dy over dt equals function, let's call that function g, because this is a different equation. It's still a function of t, x, and y, would be a system of differential equations, right? And the solution to that system would be a pair of differentiable functions, which we can consider for our sake. X is equal to phi 1 of t, and y is equal to phi 2 of t, both having the same interval I. Same interval I. To satisfy each of these equations in the system on said interval.